Hello everyone, in this video I'm going to explain how the refrigeration cycle works. Before going to the details of the refrigerator, let's try to figure out what is known as a heat engine first. Heat engine is a device that absorbs heat from a high temperature medium and do some useful work, and the remaining heat is rejected to a low temperature medium. A very good example is an automobile engine. Automobile engine generates heat while combusting fuel inside the combustion chamber and do some useful work, convert that heat energy into kinetic energy to drive the wheels, and the underutilized heat is rejected to the surrounding atmosphere through the exhaust tunnel. When it comes to a refrigerator, it is kind of completely opposite to the heat engine, because a refrigerator is a device that transfers heat from a low temperature medium to a high temperature medium. This is not the natural way of heat flow, right? The heat usually flows from a high temperature medium to a low temperature medium. Therefore, in order to make this reverse process, we need to have some sort of a work input to the device. Otherwise, this process will not work. Since we only consider about the refrigeration, since we only said that this is the refrigeration cycle, but remember that this process is also applicable to the air conditioners as well. Then we try to identify what are the major components of a refrigerator. I have shown it here in this diagram. We start from the first important component. There are 4 important components. The first one is the compressor, usually located at the very bottom of the refrigerator. The next component is the condenser, usually located at the back end of the refrigerator. A condenser is a heat exchanger. Simply, it exchanges heat from the substance that flows through the condenser with the surrounding atmosphere. The third component is the expansion valve. Sometimes it is also known as a throttling valve. In some applications, you won't be able to see a valve, but instead of that, the manufacturers simply use a capillary tube to do the expansion work. The last component is the evaporator. Evaporator is located inside the refrigerator. Evaporator is also a heat exchanger, like the condenser. While the condenser rejects heat to the surrounding atmosphere, the evaporator negotiates with the heat inside the refrigerator. When it comes to a thermodynamic cycle, I hope you all know that there is some working fluid or some substance that flows through these components. So in a refrigeration application, this working fluid is specifically known as a refrigerant. There are different types of refrigerants. For example, R32, R134A, R600A likewise. Okay, then we go to the fundamentals of the refrigeration cycle. Today, I am going to explain how the ideal vapor compression refrigeration cycle works. For your convenience, there's a very nice diagram I have put here representing all the components: the compressor, condenser, expansion valve, and the evaporator. So here, this is the TS diagram of the refrigerant. What will happen to the refrigerant? Simply, it will show you the temperature and the entropy variation for the refrigerant when it goes through these 4 components. So we start from the state 1. Before that, I think it is better to brush up your knowledge about the areas of this particular curve. I hope you remember that the right hand side portion of this curve, right, from the curve represent the superheated vapor state of the refrigerant, and any point to the left hand side represent the subcooled liquid. Any point within the curve, lies within the curve, represent a saturated liquid vapor mixture. Any point on this black color line, the right hand side black color line, represents saturated vapor, while the left hand side black color curve represents saturated liquid. Then we try to identify, okay, the state 1. State 1, the refrigerant is in saturated vapor state. and it goes through the compressor, and the process happens in the compressor is an isentropic compression. Isentropic, the entropy remains same. That is why from state 1 to state 2 we can see a vertical line. Vertical line means there's no change in the entropy. When it comes to the state 2, after the compression, the pressure will increase, the temperature will increase, and the refrigerant will come to superheated vapor state. Then this superheated vapor goes through the condenser. When the condenser, what is happening inside the condenser is an isobaric heat rejection to the surrounding atmosphere, or to the atmosphere, to the environment. So this state 2 superheated vapor will go through the condenser, rejects all its heat to the surrounding atmosphere, and it will become a saturated liquid. At state 2, once it exits the condenser, then the refrigerant is in saturated liquid state. Then it goes through the expansion process, the expansion in the expansion valve. See that the isentropic term is not there. It is not an isentropic expansion. If we need to have an isentropic expansion, then we have to replace this expansion valve with a turbine. But because of the complexity of using a turbine and also considering the economic factors, in normal refrigerator we do not use a turbine. As obviously, if we use a turbine, we can do some useful work by this expansion process. We can have a useful work output, and that can be used to reduce the work input of the compressor. But because of the reason that I have mentioned earlier, we use a very simple expansion valve which is very economical to be used in a refrigerator. Therefore, if we use a turbine, then it will be an isentropic process. Then the state 3 will become state 4. Okay, isentropic process, a straight vertical line, and it will come to 4' state. Since we are using an expansion valve, which is not an isentropic device, then the process or the refrigerant will end up at a state denoted by number 4. So you will see that this point 4 lies between the curve. That means at state 4, the refrigerant is in saturated liquid vapor mixture state. Then the last process from state 4 to state 1, that is the isobaric heat absorption in the evaporator. I hope you remember the term isobaric. Isobaric means constant pressure. So the condenser, the pressure is constant. There is no pressure drop once the refrigerant goes through the condenser, as well as when the refrigerant goes through the evaporator, the pressure will not drop. But the evaporator will absorb heat from the internal environment of the refrigerator, and this saturated liquid vapor mixture will become a complete saturated vapor once it exits the evaporator. And then the saturated vapor again goes through the compressor, and then the cycle will continue. Another important diagram that we need to talk about here is the pH diagram, or the pressure enthalpy diagram. So the process is the same, and you will see that from state 1 to state 2, that is the compression inside the compressor, and you will see that the compression will increase the enthalpy a little bit from H1 to H2, and then from state 2 to state 3, that is the isobaric heat rejection to the surrounding atmosphere. Since it is a heat rejection to the atmosphere, the enthalpy will be reduced from H2 to H3, and you will see that the line is horizontal. The line is horizontal means the pressure remains constant, because we considered an ideal condenser, in this case the ideal vapor compression cycle. Therefore, there will be no pressure drop within the condenser. And from 3 to 4, the expansion process we consider ideal expansion. Therefore, it is an adiabatic process. There will be no heat rejection to the atmosphere or the surrounding environment. Therefore, the line is vertically straight. You will not see any enthalpy change during the expansion process. But remember, in ideal conditions, right? Not in the real world. Then from the expansion process, the pressure will drop to state 4, and from state 4 to state 1, again the pressure remains constant because it is again inside the evaporator is it a constant pressure process, and it will absorb heat from the internal environment of the refrigerator and the enthalpy. Because of that, the enthalpy will increase from H4 to H1. When it comes to a refrigeration cycle, in ideal terms, the whole refrigeration cycle works between two different pressures. The first one is the evaporator pressure, this level, this pressure, and the other level is the condenser pressure, low pressure and high pressure. Then let me explain a real world example for the refrigerator with the values for pressure, temperature. We'll start from state 1. At that moment, the pressure is 140 kilopascals. The temperature is minus 19 degrees Celsius, very cold refrigerant, and the refrigerant is in a saturated vapor state. Then it goes through the compression process. The pressure will be increased up to 800 kilopascals. The temperature will be 40 degrees Celsius because the pressure will increase as well as the temperature will increase, and it is in the superheated vapor state. And then when it goes through the condenser, it will reject heat to the atmosphere and the temperature will go down to 31 degrees Celsius. The pressure will remain constant at 800 kilopascal. Then the saturated liquid is the state that the refrigerant coming out from the condenser. This saturated liquid then goes through the expansion process and the pressure will drop to 140 kilopascal and the temperature will be minus 19 degrees Celsius, and the state, as I mentioned earlier, is saturated liquid vapor mixture. This is an example of the values of the pressures and the temperatures of the refrigerant that flows through the refrigeration cycle or the ideal vapor compression cycle. When it comes to the performance parameters of the refrigerant, we define a parameter known as the coefficient of performance or COP. COP is defined as the ratio between the desired output over required input. The desired output for a refrigerator is the amount of heat absorbed from the internal environment of the refrigerator, or simply the evaporator heat absorption, or QL. QL can be simply identified or calculated by the enthalpy difference between state 1 and state 4. So H1 minus H4. The required input for the refrigeration cycle is the work input to the compressor that can be calculated by the enthalpy difference between H2 and H1. H2 minus H1. With that, remember, in domestic refrigerators, or ideally any refrigerator, usually the COP or the coefficient of performance is greater than 1. Higher is better. So that is the end of today's video. If you need to know further about the refrigeration cycle, please click the link below in the description. If you are interested in learning thermodynamics, please subscribe to our channel. Bye bye.